Well, thank you. Welcome back. We'd been talking about the medieval image of the world, the discarded image that C.S. Lewis talks about. But even in the medieval times, there was a development beyond Aristotle's picture of the universe. And it came partly because of the challenge of theology. Aristotle talked about a universe that was eternal and sort of unchanging. And it was inconsistent with the cosmology of Christianity. Thomas Aquinas worked out how you could reconcile the two. But even before him, in Paris, the Bishop Etienne Tempier wrote an edict in 1277 reminding the philosophers that there's more to the universe than philosophy. He had several hundred things that he didn't want philosophers to teach, such as studying theology is useless. You know, it's a good way to start arguments in the dinner table. But also statements such as, God could not have made other worlds. God can do whatever God wants. That's why we call him God, right? And this gave the freedom to the philosophers to challenge these ideas of Aristotle and stretch them and look beyond them. And by the 13th century, a lot of ideas are found in the writings of the philosophers. Virtually all of them are churchmen. Ideas that would eventually become part of modern science, such as John Buridan talking about momentum, Nicholas of Rheims talking about the relative motions of the earth and the sky, Nicholas of Cusa saying that every star is a world with its own universe. The Renaissance would have happened right then if it weren't for the Black Death, the plague that wiped out a third of Europe. And it took several hundred years for the population to get back to the point where it was in 1300. And that's really when the sciences finally did get going. Just an example, though, of the way the logic worked. Nicholas of Rheims, I mentioned. He wrote in a book on the Book of the Sky and the World, 1377, all motions are relative. If arrows fired to the east and west had the natural circular motion due to the Earth spinning, then you would not see any difference in flight. That was one of the arguments. The Earth can't be spinning because if you fire things one way or the other, no. If they're already carrying this momentum, then an arrow shot to the east or shot to the west will travel the same distance. And with series of reason alone cannot rule out the possibility that the Earth is spinning and the stars are holding still. 1377, 200 years before Copernicus. Then he answers by saying, this just shows you that reason has its limits, because everybody knows the Earth is standing still. He still had the cosmology of a fixed Earth that was so commonsensically obvious to him. He couldn't go beyond it. When Copernicus, in the 1500s, comes up with the Copernican system, everybody remembers the picture on the left, because that was the picture in the front of his book. And probably a lot of people looked at the book, looked at the pictures, read the titles, and then put the book on their shelf. The real system that he describes is more as illustrated here. The sun itself is making a tiny circular motion. The planets are still having these circular motions. You needed all of this in order to be able to predict accurately the positions of the planets. The one thing that you removed was one term in every equation by having the sun being fixed and the Earth going around the sun. How many people that actually read Copernicus knew this? Was this a radically counter-biblical idea? Copernicus writes in 1542, publishes. The book is dedicated to the Pope, and it is written at the encouragement of a cardinal, and because Copernicus is a good Catholic churchman. Soon after the Copernicus book comes out, at the height of the Protestant Reformation, the Council of Trent begins, and for 18 years they spend looking for heresy everywhere, and they have no problem at all with Copernicus. When it comes time to reform the calendar, they use Copernicus's tables to calculate, when are we going to actually determine what Easter is. The great thing that Copernicus did was he could explain that weird motion of the planets by saying it's not the planets going back and forth, it's the Earth moving at a slightly faster rate than the planets are moving. And that was his big addition. There was a philosophical idea that having something big and bright like the sun, did they know that the sun was big? Yeah, they did. Because they could see the moon, and they knew that the moon was closer to us than the sun because the moon moves in front of the sun when we have an eclipse. They knew roughly how big the moon was because you could see the shadow of the Earth on the moon. They could work out that however they knew how big the Earth was, the Greeks had measured this with using shadows in different parts of the Earth. They knew that the sun was bigger than the moon because it was farther away and still measured the same part of the sky, much bigger than the Earth. The philosophical idea of having the biggest thing at the center was the main thrust that made the Copernican system feel right. But how do you prove it? How do you prove whether or not the Earth is moving or the sun is moving? This was also understood well. If the Earth is moving around the sun and there are stars out beyond, that at one time of year, when you look from the Earth to that nearby star, it's going to seem to be in front of those two stars over there, but 6 months later, when you're on the Earth looking at that very same star, it's going to be in front of different stars. The idea is called parallax. If you want to get an idea, those of you in the audience, in the back, people in the front stand still. In the back, move your head back and forth. And you can see how the heads of the people in front of you shift relative to my position. Because you move, things that are at different distances appear to move back and forth in a slightly different way. And those of you closer now, you can move your heads back and forth and get the same effect. And it's called parallax. So what you have to do is observe the exact positions of stars and see if you can see one star shifting relative to another over the course of half a year. Tycho Brahe, a fellow up in Denmark, built, before the telescope, built a wall that was about 18 feet across with a giant protractor, and he was able to measure the positions of stars to within a fraction of a minute of arc. Now, what's a minute of arc? Big circle has 360 degrees, 180 degrees for a semicircle. Every degree can be divided into a minute part of a degree, and there are 60 minute parts, 60 minutes, and every minute part can be divided into 60-second minutes, 60 seconds. And he's able to measure positions to less than 10 seconds of arc. And he sees absolutely no parallax. So either the stars are so immensely far away that the motion of the Earth looks like nothing, or the Earth is not moving. 100 years later, after Galileo, great scientists like Robert Hooke, 1674. This is 40 years after the Galileo trial. He's still saying that, people, even with telescopes, are able to measure parallax to an even finer degree, and they still see no parallax. So that maybe the Earth's orb is not moving. That Riccioli that he's talking about is this guy, who was a Jesuit, Society of Jesus, writing in the year 1651, 20 years after the Galileo trial. And he comes up with a number of arguments that weighs the Copernican system and a different system, we'll talk about the Tycho Brahe system, where the Earth stands still. He's most famous, of course, for coming up with the map of the moon that we still use to this day, with the names we still use. And he includes the most prominent crater is Copernicus. 20 years after the Galileo trial. And he has craters named for other scientists who believed that the Earth was moving, including Galileo. And he puts himself on the moon as well. There are 35 craters named for Jesuits. It helps that the guy who made the map was a Jesuit. Well, a friend of mine has gone and read this Riccioli book. Break for a second as I make a horrible noise. Okay. A friend of mine has gone and actually read the Riccioli book, which is in Latin. He and his wife read Latin, and he knows astronomy. He's one of the first people in about 100 years to do this. And he discovers the nature of Riccioli's arguments, why he believes the Earth is not moving. How can you tell how far away the stars are if you can't see them move? He says, I know how to do it. You look at a star. You look at a star in a telescope, and you see the disk of the star. And you measure how big the disk of the star is, and you know how big the sun is, so you can figure out how many times further away it is if it was the same size as the sun and to be as small as it is in the telescope. This was not an original idea with him. Galileo, in his book, has exactly the same idea and works out that it's 2,000 times farther. Every star is going to be 2,000 times farther away than the sun is from the Earth in order to measure the disk that he sees in his telescope. And if the sun was a certain distance and the stars were 2,000 times farther away, by golly, you ought to be able to see that. And nobody could see it. And Galileo was writing saying, well, eventually somebody's going to see two stars close enough that we can make this measurement. Just wait. What neither of them knew is that stars look like disks in a telescope, not because you're looking at the disk of the star, but because telescopes are not perfect. Because light is actually made up of waves. If you're at an ocean and you've got the harbor and the red lines of the waves coming into the harbor, the waves going into the harbor mouth don't suddenly stop at the edge. That's not what happens. Instead, they spread out. And that spreading out you can see even in a ripple tank in a physics lab. The amount of spreading depends on how big your gap is. The bigger the gap, the less the spread. So what's the gap that waves are going through when they come into a telescope? It's the size of the lens. It's the hole at the front of the telescope. And when you plot out how bright the light is coming through the hole, even if the light is an exact point, it will spread out by a certain amount. It's named for a fellow named Airy. It's called the Airy disk. And the smaller your telescope, the bigger the spread, the less good your vision's going to be. That's why astronomers now try to make as big a telescope as they can to make it as fine as they can. But something else happens. That's the spread you get from a really bright star. That's the spread you get from a star that's half as bright. Notice that the size of the spread is the same because it's determined by the telescope. But the height is depending on whether the star is bright or not. Now the human eye, which is your detector looking through the telescope, cannot see infinitesimally faint things. It can only see a certain faintness. So let's cut off all the faint part of the light. What have you got left? Bright stars look to be bigger than faint stars, right? And you think to yourself, naively, I'm looking at a star, well, the bright star is bigger because it's closer to me. And the faint star is farther because it's farther away. No, it's entirely due to the wave nature of light that wouldn't be understood for another 200 years. So when you have photographs of stars, bright ones look to be bigger than faint ones, but it's entirely an artifact of the instrument. Remember what I said, how people were finally using instruments to see things, and they didn't know that the instrument is going to color the thing you see. In ways, if you don't understand how the instrument works, you'll never be able to figure that out. The conclusion was that the Earth wasn't moving. To every scientist who really looked at it with an unbiased view back in the 17th century. But wait a minute, didn't Galileo show that things had phases? And didn't Galileo show that Jupiter had moons? And how could you... Tycho Brahe, very clever guy, before Galileo himself had worked out this really clever system. Imagine, if you will, the sun is at the center, or the Earth is at the center, not moving, sun goes around the Earth, all of the other planets go around the sun. Now, you may recognize this is actually the same thing as the Copernican system, only you've shifted the origin point, except for what the stars are doing. This matched the data of the time. Isn't that what science is supposed to do? You come up with different hypotheses, you find which one matches the data, and you say that one must be the truth. Well, you know, the Earth being at the center of the universe looked like the truth. Besides, no one in the 17th century, at the time of Galileo, could figure out why would the stars and the planets move? Why would planets move around the sun? Why would they move in this particular... Aristotle had a way that you could predict. Nobody had a way to replace Aristotle's physics. That didn't occur for another 100 years. And the first step was not only Tycho Brahe, but then the guy who essentially claimed to be his student essentially stole his data after Brahe died. You know how Tycho Brahe died. Very sad story. He wanted to see the king of the Holy Roman Emperor, and he had been exiled from Denmark at this point, and they kept him waiting and kept him waiting and kept him waiting, and he didn't want to leave for fear that he'd lose his chance to see the emperor. And he really had to use the toilet, but he didn't want to leave, and he died of a burst bladder. So the bathrooms are back there. Well, Kepler comes along. Kepler is a contemporary of Galileo. And Kepler works out, for reasons that are marvelously bizarre, a marvelously bizarre view of the universe. Remember the medieval idea. You've got this unity of the ranks of angels with the motions of planets. Physics and metaphysics talk to each other. And Kepler is still in that mindset. But it being the time of Protestantism and everybody's coming up with their own theology, he invents his own theology. What's the most glorious thing in the sky? The sun. What's the most glorious thing in nature? God. Therefore, God is the sun. What comes off the sun? Light and beauty and warmth. That's like the Holy Spirit. Oh, yeah, got it. He's got this weird theology. And then he reads Copernicus a little more. And Copernicus has the sun doing this little circular dance around nothing. And he goes, God can't be moving around nothing. God must be fixed. How can I mathematically describe the motions of planets that allows the sun to be fixed? And he spends a few years until he stumbles across the idea of planets moving in ellipses. And he says, I can match the data. If his data had been 1 decimal point more accurately, then he would have seen all the perturbations that would have destroyed the system. But fortunately for him, he didn't. Kepler also writes in one of his books, no truth can be derived from false principles. and then uses the totally false principle of that the sun is actually God to come up with this, turns out to be true, description of the motions of the planets. Now, Kepler wrote in really turgid Latin that most people couldn't understand. Galileo had copies of Kepler's books, said, I can't make heads or tails of this, tossed them to the side, never read them. Galileo was a college dropout. He actually, flunked Latin. It's not until many years later that a fellow named Edmund Halley of Halley's Comet talks to his buddy Isaac Newton as Newton is working out these mathematical principles of how the nature works, and Newton has devised a way of describing why things would move, why the moon would move around the Earth. And Newton says the moon moves around the Earth because it's actually falling, but falling with a sideways motion, falling exactly the same way that an apple falls from a tree. And if things are falling around the sun, if the force that causes them to fall in can be described as varying as 1 over the square of the distance, then the path that they follow turns out to be ellipses. And this coincidence of the prediction of the laws of nature with the coincidence of the motions of the planets suddenly makes people, we're now into the 18th century, go back and say, here's a new physics. Maybe Copernicus was right. But it's not until around 1700 that this idea finally takes over. Now, there was a lot of curious things that come out of this. First of all, back in the Aristotelian system, you notice that the stars and the planets move forever, but things here on Earth don't move forever. If I push something, as long as the living person is pushing it, it moves. When I stop pushing it, it stops. I notice that the pyramids are rotting away in Egypt. Things on Earth fall apart. Things in space don't fall apart. I can explain this theologically. We're part of that fallen universe where things used to be perfect in the past. And that means, of course, that the Earth is not the center of the universe and the most glorious part of the universe, something that Copernicus was going to demote us from. You hear people talk about the old and the new view that way. The Earth in the medieval view was not the center of the universe. The Earth was the bottom of the universe. It was the worst place in the universe. In fact, not quite the worst place, because what's in the center of the Earth? The Inferno, where the devil lives. If you're saying that the Earth was privileged by being at the center of the universe, you're saying that hell is even more privileged. Nobody in the Middle Ages believed that. So the objection to the Copernican system was not that it meant that human beings were no longer the most glorious thing. The human beings never were the most glorious thing. The angels were the glorious things. We were down at the bottom. This new system of Isaac Newton says we're all at the same level. That human beings and planets and stars all obey the same rules. It also says that these rules are pretty inflexible. If you tell me the force acting on an object and where that object is and how fast that object is moving, then I can predict for all time where it's going to be. And by the way, I can retrodict where it was in the past. And suddenly, the universe is no longer a living object, it's a machine. Where is God in this universe? Well, if the universe is a big watch, God's the watchmaker. Maybe wound it up at the beginning if there was a beginning. Maybe God is also there to fix all the bits that I can't quite figure out. Newton was able to say, if the gravity of the sun is what holds the planets in orbit, and the gravity of the planets is what holds their moons in orbit, well then, don't planets have gravities pulling on each other, and shouldn't that upset the whole apple cart? So he says, that's why I can show there's a God, because God explains why the planets don't upset each other. 100 years later, another mathematician, Laplace, presents a new book of celestial mechanics to Napoleon. Napoleon says, you don't talk about God in here anymore. And Laplace says, I have no need for that hypothesis. Sounds like, the atheist saying we don't need God anymore. He's right. If God is nothing more than a hypothesis, a force to make my flimsy scientific theories work, then I'm back to the God of lightning again, not the God of Scripture. There was a more profound problem with Newton's idea. How many people here have actually taken Newtonian physics at university or in high school? Did you find it was an easy course? Snap? Understood it immediately? Boy, I wished you'd been in my classes when I was trying to teach it. It's hard as anything to figure out because it's such a weird way of thinking about the universe. It is frankly contrary to a lot of our common sense. And it takes a long time and a lot of practice. And as somebody once said about mathematics, you never really understand it, you just get used to it. Part of the problem is, if you think about it too long, it doesn't make sense. Everything starts out with assumptions, right? Every logical system starts out with assumptions. The logical assumptions of Newtonian physics are, we have three items, mass and location and time. And then you're going to get some kid who goes, so what is mass? Well, that's the amount of stuff that, how much it weighs. So it's weight. No, it's not the same thing as weight. But it tells you how much gravity pulls on you. If you have mass, then you can measure gravity. But what is mass? Well, it's the amount of stuff, it's the number of atoms. No, because atoms have different masses. So what is mass? It's like, shut up and don't ask. What is time? It's the thing that a clock measures. Yeah, well, what's the clock measuring? It's measuring time. Circular, you can't explain it. And if you think long enough, even what is position? How do I define this spot relative to that spot? To make Newtonian physics work, I have to have a uniform system, an inertial frame, they call it. And there is no inertial frame. There's no reason why any frame should be better than any other frame. And yet, if you don't have the inertial frame, you get the wrong answer when you do the calculations. Still, after you've studied Newtonian physics long enough, you can answer a question like this. Here's a water hose in your garden. Most people who have never studied physics, most naive people, most kids who have never had a good science background, you say, okay, what happens if I turn the water on? The water goes around and around and around and around and around, and when it comes out the hose, does it keep going around in a circle? A lot of people are going to say, yeah, it's learned how to go in circles. Those of us who have studied physics will say, no, in fact, the water goes straight out because the hose is no longer causing it to go in circles. And that's what Newtonian physics tells us. How many of you people have ever worked with a hose in a garden? You turn on the water, what's going to happen? That hose is going to go flying every which way and you're going to get soaked. In theory, with enough calculations of every inch of every hose and working out the Newtonian physics, I could probably model the motions of that hose, but in fact it's chaotic. It's crazy. Newtonian physics, though in principle seems like it ought to be able to explain everything, in practice it also has great practical limitations. And it's really hard to bend your brain around it because you're changing your cosmology, which is never easy to do. And after you spent 5 years at university in physics classes changing your cosmology, so now you take for granted things that seemed really weird 5 years earlier, then what happens? They spring relativity at you. And you discover that everything you thought you finally understood is still wrong. What's gravity? Gravity is the thing that Newton says he's describing. Gravity is what my equations describe. Why is there gravity? He says, I feign no hypotheses. I'm not going to even pretend to guess what it is. Einstein suggests that gravity is the warping of space-time. Not just the warping of space, but the warping of space-time. What do you mean warping of space-time? You can just see. Those are galaxies. But you notice the little weird circular patterns around that cluster of galaxies? When you measure the light coming from that weird thing, you realize that that light is coming from a galaxy that's behind the galaxy you're looking at. And the light from that galaxy has been passing through space that has been warped by the gravity of the galaxy in front of it and bent around into what these things are called Einstein rings. And the fact that space-time gets warped and that light follows the warped shape of space-time made the suggestion that if you could ever see field of stars that you've measured their positions precisely, and then have the sun be really close to one of those stars, the apparent position of that star would be shifted. But in fact, it would really be the space around the sun warping the path of the light. Well, you can't see a bright star next to the sun unless you go to an eclipse. 1919, Eddington observes an eclipse in South America that matches the predictions of Einstein. This is a big deal for a couple of things. Einstein's a German. Eddington is an Englishman. 1919, the war is barely a few months over. And yet, an Englishman is going to great lengths to show that the theory of a German is correct. That was a big deal. It suggests that Einstein's crazy, bizarre, wonderful theory of a universe that is far more complicated than Newton seems to describe the extremes better than Newton could. Newton's wrong. This is the headline of the New York Times article the day after Eddington describes the results of his experiment. And you see that it says some really odd things. Men of science more or less agog over the results. Einstein theory is not just right, it triumphs. Stars not where they seem to be or were calculated to be, but nobody need worry. We've got it all. A book for 12 wise men, no more in the world could comprehend it, said Einstein, when his daring publishers accepted it. Well, in fact, it wasn't even a book, it was a paper. Einstein never said that. But I remember growing up, only 12 people could understand relativity. I thought, I'm going to be the 13th. Yeah, right. I took general relativity. I'm not the 13th. The fellow who wrote this article was the only reporter the New York Times had in London that day. He was a sports reporter who was there for a golf tournament. And he reports it as if it was a sporting event. And all of the mythology of Einstein comes out of this crazy article in 1919. Interesting thing. Einstein had this intuition of physics, which he attempts to describe in mathematics, but his math wasn't all that strong. He borrowed, he worked with other mathematicians to come up with a mathematical description. Some people are really good at math. Some people are really good in physical intuition. You have collaboration so that each person can do what they do best. Eddington was really good at observing stuff, But he had a postdoctoral fellow, a Belgian, by the name of Georges Lemaitre. Georges Lemaitre had a math degree from Louvain. He could read mathematical equations the way that you might be able to read a piece of poetry. Reading the mathematics of Einstein's general relativity theory, he gets an insight. He goes, you know, if there is gravity everywhere, the universe is warped by mass everywhere, then if the universe were infinitely old, everything should have been warped together into one big lump by now. And that didn't happen. He also knows that about 20 years earlier, a fella had noticed when you observe distant galaxies, they seem to be moving away from us. Their light is shifted to the red, which means that they're moving away. He says, I can explain what's going on in terms of the math if the universe is expanding, which is what you see in the math as a possibility. And if that were the case, then if only you could measure how far away the galaxies were, then you'd see a correlation. The ones that are the farthest away are the ones that have moved the furthest in a particular period of time, because, if you run the clock backwards, all of the mass of the universe would be in one point at some time, which we could calculate by seeing how far it's moved since then, how fast these things are moving now. And indeed, because the universe is made out of this space-time fabric, which is different from the inertial plane of common sense, it's not that the universe is moving out into Einstein's inertial frame. It's that the framework of the universe itself is stretching and getting bigger. And all of space and time is contained in this point. Now, this is the same time that quantum theory is coming up. Quantum theory that says that the universe is made of individual bits, not continuous fields. So there's Millikan, the guy who showed that electrons were individual bits and not a fluid. And there's Einstein, who talks about general relativity, but also showed that photons, light, come in individual bits. And in between is Georges Lemaitre, who goes off and gets a second degree PhD in astrophysics at MIT, and writes up this little paper in French, because he's Belgian, which his buddy Eddington translates into English. The quantum theory says that there can be quantum states of very high energy. Lemaitre says, what if the entire universe starts at a time zero at an infinitely high quantum state that we will call the cosmic seed, the cosmic egg? And we can, if we can observe the galaxies, we can even calculate when that time would have been that everything starts. The astronomers are horrified, because the astronomers for 100 years have been saying the universe is constant and the same physics here is there as ever. This violates one of the assumptions of our cosmology. And besides, notice the collar that guy's wearing? He's a Catholic. He's a Catholic priest. He's just doing this to come up with a way of getting Genesis back. He was not a Jesuit, by the way. I just want to let you know. A lot of people say he was a Jesuit. He was a diocesan priest. It is possible to be smart and be a diocesan priest. just to let you know. Fred Hoyle, one of the great cosmologists of the day, looking at the data, because soon after Lemaitre says this, Hubble actually shows that the universe is expanding just the way that Lemaitre predicted. Fred Hoyle comes up with a totally different cosmology to try to explain the same details. Gets on the BBC, he's one of these public astronomers, and he says, my theory is so much better than Father Lemaitre's Big Bang theory. The name Big Bang was given to the theory by somebody who didn't believe in it in order to make fun of it. by an atheist who thought the Big Bang Theory was too religious. A couple of things happen later on. Further observations, a whole bunch of things I can't even get into at this point, show that Hoyle's idea is wrong, Lemaitre's idea is right. And Hoyle and Lemaitre actually meet at a scientific meeting at the Vatican in 1957. Hoyle, the viciously anti-clerical atheist, and Lemaitre, the priest, they become best friends. Because they're both interested in the same stuff. They go on vacations together. Another thing happens, by the way. 1951, Pope Pius XII, who was something of an amateur astronomer, hears about all of this, gives a little talk to the Pontifical Academy of Sciences saying, isn't it interesting that geologists are talking about the Earth having a finite age, and the cosmologists are talking about the universe having a finite age? Isn't this really wonderful? You know, this is not a surprise to any of us who have read Genesis. Father Lemaitre goes to the Pope and says, don't say that. Because the creation of whenever the Big Bang started is different from the creation that happens by God creating out of nothing. More recently, Hawking wanted to come up with a gap that said, I can explain the Big Bang without God starting things. It's a fluctuation in the space-time continuum, a fluctuation in gravity. Therefore, there is no God, which is kind of weird logic because Hawking is saying, to him, God is the thing that started the Big Bang. And then he says, no, gravity is the thing that started the Big Bang, which is not that there is no God, but rather that God is gravity, which is kind of weird. But then maybe he thinks if God is gravity, that's why Catholics celebrate Mass. The trouble is, if God is just something that fills a gap in your knowledge, then he's no more than a law of physics. It's not the God of Scripture. It's not the God who created outside of space and time. God did not create the universe 13.8 billion years ago. He's creating the universe right now, at every time, in every space. Creating a universe that is really out of nothing, not just in a vacuum, but in a universe that didn't even have space, didn't even have time, didn't even have a fabric, didn't even have, this is the book of Maccabees where we first get the idea of creation out of nothing. And to skip ahead to a universe that only operates by Newton's laws of physics is a universe that doesn't have room for the transcendent things that are also part of our universe, including beauty, including wonder, including the very things that make us want to wonder about the universe. In any version of the universe that tries to simplify things removes the very things that makes the universe worth studying. The universe that we see is made truly from nothing by a God who creates at all time, in all places. A universe that not only is rational and logical step by step the way it's done in Genesis, but has an extra added feature that no one could have guessed. It's a universe that's beautiful. It's a universe that's full of wonder. It's a universe that's full of love. If we didn't love it, if we didn't love the wonder, if we didn't love the rationality, not only could we not explain the universe with science, we wouldn't want to. We'd be back to the Romans, just explaining things with nature gods. But our God is not a nature God. Our God is supernatural. Thank you very much.